Okay. I have a little video at the beginning. We'll see. We'll see how it runs. It kind of gives you some review from last section last week and a little bit of a look into the rest of section 1. I have a nasty cold. I'm going to cough a lot and spray stuff in my throat a lot. If I get too quiet on you, please let me know. If you can't turn up the volume enough to hear me, and we'll try and last through the evening. Any questions before we start? Everybody is ready to go? We're going to do chapters 8, 9, 10, 11, then jump to 14. 14 is more related to 11 than it is to anything else in the book. It's lighting, so we'll have a look at that one. This evening. Let's see if this is going to run.
The modern commercial or office building consists of many sophisticated systems. These systems include foundation and support structures, electrical and lighting, and plumbing and fixtures. Another major part of any building that is often taken for granted by its inhabitants is the HVAC system. HVAC stands for heating, ventilation, and air conditioning. In this unit, we will identify the purpose and goals of the HVAC system, describe basic HVAC parts, and describe how these parts work together. Air quality is an essential consideration in maintaining the productivity, comfort, and health of the occupants and should not be trivialized. If air quality and temperature are not maintained, occupant comfort in the workplace can suffer, directly affecting productivity and morale. The goals of an HVAC system. When examining the design of an HVAC system, we must remember the various roles that the HVAC system plays. We all know that when we're cold, we turn the thermostat up for more heat, and when we're hot, we turn the thermostat down. So the HVAC system keeps us comfortable by adjusting the room's temperature. But equally important, the HVAC system must keep occupants comfortable by supplying fresh air to a room. If we introduce a significant proportion of fresh exterior air and alleviate carbon dioxide buildup, occupants experience better health and performance gains. Studies have shown a direct link between CO2 levels and short-term sick leave in office workforces. However, our concerns regarding the HVAC system and occupant health do not end here. In heavily air-conditioned, energy-efficient environments, recirculated conditioned air can carry contaminants which contribute to respiratory illness. It is the HVAC system's job to remove contaminants and dust from the air using filters at various stages. As important as this consideration is in an average office or commercial building, this feature is critical in facilities that contain clean rooms, medical facilities, or hazardous materials. Finally, with the spiraling cost of fuel, HVAC systems must also be efficient and economical. Energy-efficient HVAC systems might incorporate variable air volume designs, components designed for operation at low pressures, digital control systems, mechanisms for reclaiming heating or cooling benefits from recirculated air, and high-efficiency ECM fan motors. Many priced products are designed specifically with energy efficiency in mind. By understanding the importance of occupant comfort, we realize the significance of the HVAC system in a building design. It's responsible for controlling the temperature in the environment, providing fresh air to the occupants, filtering out dust and contaminants, while operating in an energy-efficient and unobtrusive manner. The following section covers the different parts that make up a basic HVAC system. Once we understand the range of components involved, we can better understand the reasons for choosing system components from Price's extensive product line. The parts of an HVAC system. The HVAC system installed in a commercial or office space differs greatly from the heating and cooling system that you might be familiar with in your house. In your home, your heating system is set up to deliver warm air during the winter and cool air in the summer. It does this using a furnace or an air conditioner and a common set of ductwork. When your thermostat detects that your home is too cold, it sends signals to the furnace, which then delivers warm air simultaneously to all parts of your house. Note that it is typical to have only one thermostat, and it does not account for temperature variation in any other rooms. Likewise, in the summer, your thermostat will detect when your home has become uncomfortably warm, and it will signal your central air conditioning system to deliver cool air simultaneously to all parts of your house. Again, note that your thermostat is measuring the temperature in only one room. The conditions in an office or commercial space are quite different. Higher concentrations of people and equipment will generate more heat, making air conditioning or recirculation of air more important than providing heat. Although the air handling equipment is centralized, different rooms and regions in the building will have different needs for heating and cooling. These needs are called loads because they place a load or demand on the HVAC system. These loads can come from equipment, people, weather, and many other factors. In the simplest case, we address this by providing a constant supply of cool air, which is then managed by the HVAC distribution system. The chiller or air conditioner utilizes heat exchangers and circulated fluid or gas to cool the air that is passed through it. The air handler is a fan or a blower that moves air throughout the building's ductwork. Axial or centrifugal fan types may be found in the air handler. Air filters. Depending on the requirements of the occupants and the activities in the building, various grades of air filters are used in the system. General purpose air filters will be included in the air handler itself, while more sophisticated filters, such as HEPA filters, may be used in the downstream ductwork. Ductwork. Round, square, and rectangular ductwork provides a pass for the conditioned air from the air handling unit to the environment. A damper consists of one or more blades which can be used to control the amount of airflow through a duct. Manual dampers are used to ensure that different parts of the building receive proportional ventilation based on area and demand. Automated dampers may be installed at firewalls which close in the case of a fire. A terminal unit is a device that uses an automated damper to control the amount of air which is delivered to a room or region. The damper is typically controlled by an electric, pneumatic, or digital actuator, which in turn is regulated by a thermostat. A set of adjacent rooms or regions in a building which have identical heating and air conditioning needs are called a zone. It is typical to assign at least one terminal unit and corresponding thermostat to each zone. Price manufactures many different varieties of terminal units to suit all types of building needs. We discuss terminal units in greater detail in the forthcoming terminal units section. Heating coils may be installed after a terminal unit to provide heat on a zone-by-zone basis. As mentioned previously, buildings with a high number of occupants may not require extensive heating even during the coldest months of the year. Heating coils offer an efficient way of providing heat for those few areas that require it and are controlled by the same thermostat system as the terminal unit. Various types of linings are available to dampen noise within a duct. A short length of line ductwork called an attenuator is often installed following the terminal unit to dampen discharge noise. Ultimately, the test of an HVAC system lies in its ability to deliver conditioned air to the occupant. Air from the ductwork enters the occupied space through grills, registers, or diffusers, often called GRDs.
Ito na naman yung nagko-connect eh. Paano ito i-testing? Lagyan mo ito ng power para gano'n siya. Okay. Test mo dito.
The term grill is commonly applied to any air outlet or intake that consists of a square or rectangular face and neck and whose facial appearance is made up of louvers, which may be used to deflect the air. A register is a grill that has one or more adjustable blades or dampers that control the amount of air that flows through. A diffuser is an air outlet which incorporates structures such as vanes, louvers, perforations, and other features for distributing and directing air. The diffuser's job is to direct the airflow throughout the occupied space in the most efficient manner possible. More information on desirable air patterns is provided in the space air diffusion section. We will discuss diffusers in more detail in air outlet selection. Once air enters a space, where does it go? Air circulates through the return inlets and returns to the air handling unit. Unlike an air outlet, a return requires no sophisticated vanes. However, the relative location of the air inlets and outlets can be critical to the efficiency of the system. Upon returning to the air handler, a certain portion of the return air is exhausted and replaced with fresh exterior air. In an average office building or commercial space, approximately 10 to 20%. For an interactive look at an HVAC system in action, experiment with the activity provided here. Use the thermostat shown to rate.
It's hot enough to cook an egg on my desktop. Somebody ought to open a window or something. I don't know about you guys, but if it gets any hotter, I'm going home. Give us a break. We're roasting in here. Is it just me, or is it hot in here?
Okay, you get the idea. I'm sure you all experienced somebody wants it warmer, somebody else wants it cooler. It's always a battle. You work on a.
You suggest? Oh. Leaves.
Okay. So some of that stuff was covered last couple of classes. Some of that stuff's going to be covered tonight, and I think all of it is pretty darn applicable. So starting with ventilation, V and HVAC, heating, ventilation, air conditioning. So we started with heating in the first chapters of book 2, all the different ways to warm people up. Talk briefly on ventilation, and then we're going to touch on some methods of ventilating, bringing in circulating some outdoor air to freshen things up. Video pointed out that that's a very important aspect of what we do in this field, HVAC. And when we get into air conditioning, be careful with the terminology, because we certainly condition air, and it doesn't always mean that we're just cooling it. As much as we say air conditioning, when we mean cooling, we're also talking about heating and ventilating and filtering and different kinds of filters. So all of those kinds of things are happening with the equipment that we're going to look at. So methods to ventilate and exchange air, bring in some outdoor air instead of recycling the same stale air back around and around everybody. Back in the day, we had, I need my highlighter going here. Back in the day, we had something called natural ventilation. And what that meant was we often had windows and doors that weren't that tight, and there was some leaks and cracks anyways. If you wanted some more fresh air, you just simply open A window, this is not a efficient system. It could cause drafts if the person that was feeling too cold in a room was sitting across from another person that wanted to have the window open. They could have a draft, cold air blowing on them. And simply opening a window does not reliably or necessarily remove the stale air. In newer buildings and that come under newer building codes, they have requirements for ventilation. I think chapters in the beginning of book 2 had some calculations and charts for all that stuff. We're just going to talk about how we make it work in the future chapters here. With a fan, we can ensure that we have proper ventilation and minimum flow rates, make it all happen. When we distribute fresh air or ventilate, air should be distributed evenly to prevent pockets of stale air. And when we consider we're talking about comfort of occupants, we don't want this air to just be drawn in and blowing on the first person in the side of the building, right? So you're going to see a lot of equipment that looks pretty strange and wonderful and does all kinds of strange things. As the video pointed out, there's some various ways to introduce the air. Remember, we have 2 main methods of ventilation: the natural type, air movement created by wind or temperature differential only, no fans, or mechanical. And mostly we will look at mechanical. We'll touch on natural a bit, and then so air movement created by some equipment, and the equipment for creating air movement is fans and blowers. Building codes require fans. There's minimum requirements: how much air, how many cubic feet per minute must be exchanged, what are all the things going on in the building, and then calculations are made. In the simplest system, home exhaust fan, if you have a newer home, this stuff is not in my home. If you've upgraded an older home, you will have connection with the heating system blower. So a warm air heating system will be connected to the switches for exhaust fans over the stove and in the bathroom. When the exhaust fan in the bathroom is started up, the blower in the furnace will start, and that means it's going to bring in the fresh air as we exhaust the air from those areas, from those rooms. So when the exhaust fan comes on, furnace blower starts, ventilation air enters at the same rate, approximately the same rate as the air is exhausted. So we don't create pressure differentials in the building that can cause us some grief. So different combinations of natural and mechanical are out there in various forms. Mechanical or natural air intake and mechanical exhaust. So a blower in your kitchen, a blower in your bathroom are turned on. That's mechanically exhausting air. So in my system, without that connection to the blower, I'm just simply going to have to rely on natural air coming in. Some systems are built with ventilation fans, a mechanical air intake. If you have some kind of a shop where there's welding and fumes, and maybe an automotive shop where cars are possibly going to run in there, you're going to need mechanical air intake, and it could be just a natural exhaust. And this is approximately the same as draft for a furnace. We have an induced draft fan pulling the exhaust out of the boiler, and then naturally air is drawn into the intake. And then this one here is a forced draft fan, mechanical air intake, and the exhaust just finds its way out through louvers and vents. And this is equivalent to balanced draft for a boiler. We have a fan bringing air in and a fan taking the exhaust out. Natural air intake, mechanical exhaust. Stale air is drawn out of the rooms by a motor-driven fan or blower, replacing fresh air from open windows or ventilating ducts. And this air is not heated or filtered, just comes straight into the building. Problem with this kind of a system is we could have a back pressure created, which can cause CO to come, draft to come back through the chimney of the furnace and cause CO when the furnace starts up back into the living space. And this is a dangerous situation. So different duct systems. Here's a fan at roof level. We've got some kind of an exhaust fan blowing air out at the roof of the building and different ducting. And they had a really good representation of this in the video where the draft exhaust air is drawn out of the system. The other method, number 2, mechanical air intake, natural exhaust, fresh air forced into the building by a blower fan, creating pressure above atmosphere. So this is positive pressure, and that will cause the stale air to move out through the windows or outlets in the walls of the roof. Air can be supplied by a fan mounted in a wall. There's no filtration or heating. This is the fan in the wall. Air can be supplied by fresh filtered air ducted to the warm air heating system, connected to the return air duct or plenum. And then method number 3, mechanical air intake and mechanical exhaust. So before these 3 methods, we talked about a furnace fan and a warm air heating system. That would be our mechanical air intake. So we start that fan and it's drawing in a controlled amount of air into the system at the same time as we start the fan in the kitchen and or the bathroom. And the fans or blowers supply the fresh air, remove stale air from the building. Different combinations of supply and exhaust methods available with different types of fans and ducts. Properly designed mechanical ventilation system will supply a controlled amount of filtered, and what tempered means is we're heating or cooling. Some of the systems we're going to look at, we're heating and cooling at the same time, and so we use the word tempered. Sometimes we're making it a little warmer, sometimes we're cooling things off. The video talked about a building with lots of people in, even in the coldest months, you're probably going to be cooling more than actually heating because the loads in the building are creating most of the heat. But that's hardly ever the case in Alberta, right? And all in the interest of making the building comfortable for the people inside. So here's an example of a system with mechanical intake and mechanical exhaust. So we have a roof fan extracting air from vents in the ceiling. So they're going out through the fan, blowing outside. And then we have also a fan in our air handling unit. We have an intake. Air is coming in, it's being heated and filtered and circulated through all the ducting in the different zones. And filtering air. So this is also very important. Of course, importance of ventilation is probably higher than it's ever been. During and subsequent to having COVID happen, all kinds of strange and wonderful things flying around in the air. Are they coming into the buildings? Probably not coming in from the street, but coming in from lots of people, so we want to ensure that we have efficient and effective ventilation. We want enough fresh air coming in to sweep those things away that we don't want, and then the other side of it is filtering and cleaning the air while we've got it in our buildings. So sometime, and there's actually going to be a little bit of homework. There's a chart on 8-7, and this is the chart, and then I've drawn a line here on this chart. So take a look at where that line is. And if you have a highlighter, that's great. If you just have a pencil or a pen, kind of indicate where that line is. And the homework will be is, why did I draw a line there? What did I want to point out to you? And we're going to have a little conversation now about different sized particles and different types of filters. That's what this is all about. We've got different filters up here. We've got what things are solid, what things are liquid. Speed of air, we're not going to discuss that much. But you will know that certain filters are applicable to certain sizes. So notice the sizes are along the bottom here. And then there's some relative mention of, is it visible or not? So as we go through this this list and look at them in more detail, you should be able to figure out why I put this line right here, okay? And what that means. I hope it helps you get some of these things straight when it comes to next Thursday night. So cooking odors, they come under vapors and gases. Fogs are called liquids, so liquid impurities. Spores and bacteria, these are living organisms. So these are the important ones right now. We're really going to be making sure we're not concentrating or collecting bacteria. We want to get rid of that stuff in different ways. Lint is solid particles, and what does this mean? It means we can see them, they're visible size. And then fumes are also solid particles, but a different size. And this has a little bit to do with where that line is. So let's go back. So notice there's visible over here, visible to naked eye. So this is big enough to be seen. And anything on this side is going to be too small to be seen. That's a hint to the answer. Air filters. These are devices that clean the air. We have mechanical air filters to remove solid and liquid particles. If you go back to this chart, you're going to see solids indicated. You're going to see liquids. You're going to see on the top different kinds of filters, which are the best ones for which of the things down in the body of that chart. We're also going to look at charcoal absorbers. They remove gases and vapors. We will also look at briefly at things like activated alumina. This is media that will remove corrosive gases. So when I worked at Fort Hills, we were commissioning little remote operating buildings. Each area had its own little control room here and there throughout the site. I mean, there was a major central control room in the main building there, but smaller ones out and about, sometimes called permit shacks, but a lot of operational communications going on, and a place for the guys working in that area. They didn't have to be 20 miles away from where the main control room was, or their equipment they were running. We'll see a lot more of this in current systems. These have been around for a while. I have one in my in my furnace. It seems to do a really good job. Ultraviolet lamp. The textbook says ultraviolet lamps remove bacteria. I sort of disagree. The filter removes it, and ultraviolet light will destroy it. It will kill it. Okay, so we'll call it removal destruction. Okay. Mechanical air filters have different classes. We have something called throwaway or disposable. These are your basic air filters. You're going to buy cheap ones. You're going to put them in your furnace or your ducting at work, and then when they get dirty, you're going to throw them away. More and more, we have this. We like to be renewable and have less garbage. So certain types of filters can be cleaned and reused. Take the filter out, take it somewhere, clean out the dust and particles, and then reuse that filter material. Filter changes in a building can be pretty darn expensive, right? And everything is just getting crazy. So the basic air cleaning device, a dry air filter. Dry filters have matting or tangled filter materials such as fiberglass or cellulose fibers in some kind of a frame. They're cheaper, they're inexpensive, not necessarily great dust holding capacity. The matting will trap the dust, some dust and things like dirt in corrugated surfaces. Dry air filter doesn't mean throwaway. Typically they are, but they could be made of some kind of wool felt or cellulose felt, and then vacuumed or cleaned or dry cleaned or washed out to replace them. Dry air filters. Some important points about dry air filters. Matting or fine tangled filter material, fiberglass or cellulose in a frame. Dry air filters are inexpensive, but often the dust holding capacity is lower, other than certain special types that have great surface area. Matting traps the dust and dirt in corrugated surfaces, and some types are reusable. Wool fill, so we can vacuum or blow or dry clean to reuse the ones. Remember that an air filter is generally some kind of a device for the removal of solid and liquid particles. Okay, we go back to our chart, you'll see that some things are called solids and some things are called liquid, and then there's a category in between that has living organisms, and we'll have a closer look at what that means. Disposable or reusable. So two types of air filters. Dry filter, this one is, you can see that this frame comes apart and you can replace the media. So this is reusable. Sorry, this is disposable media, but we keep the frame and change out the media. Another way to do that is a rotating filter. So there's a roll of filter material in one end of this device, and it will roll across. And it can be on a timer, it can be on a pressure measuring equipment. So pressure on the downstream side of a filter gets lower and pressure on the upstream side gets higher. I could turn on this transport for this media and move clean media into the revolving frame. If this type of filter has viscous media, we've yet to talk about what that is, it won't be washable. This material will roll over to the other side And then when that's used up, we'll take that out and throw it away. Bag and wedge type, they look like this. So these are dry media. And these are generally washable. These bags will go be taken out and vacuumed and or washed and then replaced. And we call these bag and wedge type. So because of the increased surface area, so they're wedges of cloth or paper material. This one has bags. These are multiple bag house filters that I'm familiar with are about 4 to 8 feet long, and they're about 4 inches in diameter. And there's hundreds of them in a filter frame like this. They're called a bag type. And these ones use some kind of a pre-filter. So there will be a filter like this on the front of these guys. And then these guys will have increased dust holding capacity over other dry types of filters. A bag and multi-wedge air filters are normally equipped with some kind of pre-filter. Viscous impingement, commonly used now when we're talking about dust and pollen and bacteria and stuff, we're going to treat or condition the dry media. Might be glass fiber, some kind of metal, fuzzy metal, copper, aluminum, wool, crimp metal, and coated with a viscous sticky fluid. And this increases the efficiency for dust and pollen removal, available and disposable, available and cleanable, and also the roll type filter media. Throwaway type, if it's viscous impingement, it's just simply material mounted in a cardboard frame, faces with wire on them to prevent the media from getting out. So this is a disposable viscous filter. So we've got a grill or a grid of some material on here that keeps this thing all together. Various sizes. So these guys can be the 16 by 24 for your home furnace, or 36 by 36 for big industrial HVAC systems and everything in between, right? If it's cleanable, it'll have a better frame than this one. This one is pretty flimsy cardboard. If we are going to reuse it, it's going to have a better frame. Media can be washed in solution, then dried, and often it's possible to spray on the viscous treatment to make them sticky and better for collecting pollen and such. And roll type filter media is just simply disposable. And they could be mounted vertically, horizontally. Doesn't matter. Someone have a question?
What was that?
Can't see who's not muted there.
What's going on?
Can see who's not muted.
Sorry.
There, good. Thank you. Viscous impingement filter. So not the best picture, but this would be a reusable one with a more sort of robust support on it for being reusable. And we're going to look a little closer at a couple kinds of electronic air cleaners. So this kind of evades a lot of students. Two distinct types. Electrostatic precipitators is one type of electronic air cleaner, and charged media is a whole different type. Some similarities. We use high voltages to attract dust and things to these these filters, but there's some important difference. Electrostatic has little or no airflow. This is a filter that creates an electrostatic field in a duct. It has some wires or plates, and they're charged with a high voltage. And when the high voltage is present, dust will come in and be attracted to the wires and the plates and stick to the insides of the electrostatic precipitator. Air will flow through, easily flow through. Should this thing fail, the high voltage system stops, doesn't work, or there's a power bump, the unit will not filter. It stops that attractive force, but there's no little or no air resistance. And they're considered to be the best for the very fine dust, smoke, and fumes. I'm just going to mark down this slide number for a typo. Charged media is a little bit different. It's very similar, but it has a media that filters air from the air, filters dust and dirt from the airflow. It also uses a high voltage field to attract and make itself more effective, but important to note that the higher airflow resistance is there, and if the power turns off, it does continue to filter because there's a media trapping the dust. So electrostatic is just an electric field, attracts dust to the inside. I had one of these in the system in my home a long time ago, and it seemed to work quite well. We pulled the plates out of it and just clean them in the dishwasher occasionally to wash off the precipitators. So precipitators are dust particles are charged in inside of a high voltage grid, 12 to 13,000 volts DC. Charged particles cling to a bank of metal collector plates that are arranged parallel to the airflow. Those plates are cleaned by washing. If the power fails, there's no filtering. Air just goes right through and no effect on the dust. These are considered the best for dust and smoke and fumes, and often used in hospitals and large buildings. We're also going to look at air washers, and this is kind of a random slide I started to work on tonight. We'll keep going on electrostatic precipitators. So these are plates, and airflow goes between the plates. And this one shows a baffle or a light filter on the front of it. I just have to close my door here and get some chatter in the background. Uh-oh. That was not intentional. I think someone's playing around. Please don't play with my slideshow. Okay. Where were we? Precipitators. Here, approximately right here. So electrostatic precipitators, to repeat, we've got charged plates. The airflow goes through these guys. It's dirt is collected on the plates. These plates come out for cleaning. They collect the dust and dirt. Considered best for fine dust, smoke, and fumes. Called electrostatic precipitators. Charged media is different. Charged media has wires in here that are charged with, this one indicates 15,000 volts, but also has a media. And the media continues to filter should the power shut off. So here's our charged media with some plates and pre-filter and after filter. And dirty air comes in, collects all the dirt, and clean air comes out. And we still need to take this media out and throw it away, okay? Charged media will remove fine dust, mists, unburned smoke, particles, and other material that will pass through dry or viscous filters. Offers resistance to airflow because of the media that's in the airstream. It's got this paper element in here that resists free flow of air. Dust particles charged by 12,000 volts. I think that picture said 15,000, so 12 to 15,000. Contaminants trapped by the media and continues to filter when the power fails. All right, any questions on charged media versus electrostatic? And there is a type of filter now. It was popular a few years back. I think I still see them. They're called electrostatic. They're not connected to high voltage. They use static electricity. It's a plastic grid. And it has the effect of being electrostatic, and they're washable. So we're talking about electrostatic precipitators. We're not necessarily talking about an electrostatic type air filter. Okay. Other devices, odor absorbers, material that imbibes some amount of gas or liquid, can be said that the material has absorbed that material. So there's terms here, terminology, adsorption. Filters of activated carbon in canisters, flat plates or pleated frames, ductwork are used to absorb odor causing gases. And these activated carbon filters like this can be, the media can be heated up to remove those gases and then reused. It's not quite the same as cleaning, but it regenerates the activated carbon. Ultraviolet light. So this is the one I have in my furnace. The electrostatic type high voltage grid creates a lot of ozone gas. It modifies the oxygen molecules. If you've ever been outside and there's been a lightning storm, there's that distinctive smell of ozone. Back in the day, we had television sets that were gigantic boxes full of tubes inside. When we fired those guys up, we could smell the ozone from the high voltages in there. So probably most of you don't remember that, but the smell of the distinctive smell from lightning is the ozone that's created from high voltage sparks. So that stuff can be problematic for people with asthma. So we took that electrostatic filter out and we added in an ultraviolet light to kill bacteria and viruses. And I swear by using this in my furnace, it keeps the number of germs flying around in the house down to a minimum. And these are used in hospitals and things. Logan, can you mute your mic, please?
Yeah, I just wanted to say, I remembered the word. Instead of kill, it's deactivate. For bacteria
good.
and ultraviolet.
That's good. That's excellent. Yeah, I say destroy, and the book says remove. And
in water treatment, we like specified deactivate rather than kill.
I like that. That's a good word. So ultraviolet will deactivate viruses and living things. Air is sterilized. So this is supposed to sterilize And we use it in hospitals and food processing and in our own homes if you have one. It's a cheap device, goes in really easy, $150. I put a new bulb in mine every 2 or 3 years. I run it all the time. You can connect it to go on with the fan. I run the fan all the time. And the bulb is 40 or $50. I shouldn't have said that because they probably just went up to 375 or something. Chem absorbance, so activated alumina, similar to the activated carbon, will remove H2S, SO2, and chlorine from air. If I talked about I started to mention the little operating buildings out and about in the Fort Hills plant. So they have an air system on them that will completely recycle air and has these chemical removal cartridges. Should there be a release, an emergency situation. And then those guys are also equipped with breathing air should things get really bad and they find themselves in the middle of some kind of nasty gas cloud. So these are additional devices that can be added. So to sort of review what we're taking out of the air contains contaminants. We should have by now figured out that most of these things are some kind of a bad thing or contaminant. Solid particles of visible size covers things like dirt and lint and pollen and insects. Solid particles of microscopic size, so still solids, but very fine dust and fumes and smoke. Liquid impurities covers mists and fogs and small droplets of chemicals. If we have vapors and gases, this will probably come from odors such as cooking. Human body can create its own odors, and some of these buildings are housing animals. So, and then in all of the buildings, there's going to be living organisms such as bacteria and spores. A little review of the chapter. Air filter is an air cleaning device for removing solid and liquid particles. Bag type and multi-wedge dry filters use a pre-filter. So here's the wedge-shaped bag filter and the bag-shaped baghouse type filters. Pre-filters to pre-filter the air. Ventilation, different methods. Remember, mechanical and natural. So with a fan and without. Pressure created by mechanical air intake, natural exhaust will be slightly higher because this is a forced draft type situation. We're pushing air into the building, so pressure is going to be higher than atmospheric. Living organisms that must be removed is the bacteria and spores. Cooking odors are vapors and gases. Fogs are liquid impurities. Spores and bacteria come under living organisms. Lint, solid particles, visible size, and fumes are solid particles of non-visible or microscopic size. Air cleaning devices, dry filter is inexpensive, low dust holding capacity. Charged media will filter if power is lost, but there is airflow resistance. Viscous impingement is effective in removing coarse dust and pollen, but if there's a lot of lint, it will quickly clog this type of filter. And electrostatic precipitators have low air resistance. If the power fails, they won't continue to filter. And this is the same list, okay? So remember, repetition, pretty important. Match these up, okay? Mechanical filters in broad classes, throwaway or renewable. So we either get them dirty and throw them out, or we clean them, reprocess them, or use them. bag type, multi-wedge type dry filters need to have a pre-filter. Roll type viscous and pingent air filters are not washable. Electrostatic, efficient in the removal of the fine dust and smoke and fume. So that's electrostatic. That's charged grid, no filter media. And there's electrostatic. Ultraviolet light, remind me the word inactivates, deactivates.
Deactivate.
Deactivates. I'm going to write that down this time. I like it. Deactivates. So do you have these filters in your building, Logan?
Yeah, that's for water. We use UV.
Oh, UV for water treatment.
Yeah, give it UV before you hit it with chlorine.
Yeah. We used to have chlorine, and then they were trying UV, but 35 years ago, they weren't having a lot of success with that, but that was sort of new technology. So here's the chart on book 2, chapter 8, page 7. Make sure you're familiar with it. I showed you a place to draw a line on there. I'd like to hear from you on Thursday about what the significance of the line on the chart means to these different kinds of things we're going to remove with the filter. A repeat, important things from this chapter: low air resistance, no filtering during power failure, that's electrostatic. Precipitator, electrostatic filters are very efficient in removing fine dust, smoke and fumes, and will filter if power is lost is the charged media type. And I'm going to change this one to deactivate. Ultraviolet light will deactivate bacteria for sure, probably spores too. Hey, any questions on chapter 8? I'm going to do something a little unusual here. I'm just going to take a break for about 2 minutes and I'll be back. And we'll dive right into chapter 9. Okay, now I'm unmuted. How's everybody doing? All good, not so good? Other people are sick?
Good, thank you.
Awesome. Awesome, good stuff. Any questions on that filter? Air filter chapter. So we looked at several kinds of heating in the beginning of book 2. Steam heating, hot water heating, warm air furnace systems. And now we're going to look at some unique heating systems that kind of tricky to classify, but for specific kinds of heating. So chapter 9, infrared and electric heating. We'll look at the application of infrared heating, describe construction and operation of gas-fired. So remember, we talk about infrared heating. It's not always fueled. It's sometimes gas and sometimes infrared. I'll try and keep it straight. Infrared electric heating installed in areas where other kinds of heating, so all the kinds of heating we looked at are not the best for certain applications. The heating applications that we looked at are good if you have areas where people are filling up the areas, classrooms, hospitals, buildings, living areas. Some of the buildings we're going to look after are great big gigantic warehouses, and this goes right up to hockey arenas and things like that. So those are not the best systems. So we have alternate arrangements for infrared, and this will be installed in areas where the other types of heating are undesirable or uneconomical. The thing about radiant heating, it's created by these infrared waves. If we burn gas to create infrared or electric heating, it's still radiant. These are invisible waves that radiate in straight lines through the air. And the example of a hockey rink, we don't necessarily want to warm the entire building. We just want to warm the people in the stands or on the bleachers. We don't want to heat it up to 72 and melt the ice in the hockey rink, curling rink. Just enough for a little bit of comfort for the people that are in the buildings. So by using infrared gas or electric heating, we have invisible waves that radiate in straight lines. And instead of warming up the room or the space, it warms up the people, it warms up the floor, warms up the stands, and keep everybody somewhat comfortable. Usually mounted overhead and directed downward towards the floor, used to heat large areas and or just specific spots. So for example, we have large buildings with high bay structures like warehouses. We'll use infrared heating. A car wash comes to mind. I was in a large car wash out here in West Edmonton. They have infrared heating. The radiant energy warms the floor. You're comfortable in there, but they're not spending a lot of fuel on keeping the whole airspace heated up in the building. We can also have spot heating used for bleachers and sport facilities and loading docks. Very large warehouse might have tens of thousands of square feet with no people generally working in the warehouse. They work at the dock at the edge, and there's more heating in that area because we have big doors that are open and closed. So we have spot infrared heating to keep that area a little. And generally, these are areas that are open to the outside atmosphere. So on the right here, we have a hockey arena with the infrared overhead heaters. And on the left, we have infrared heaters, kind of an old school factory. These are gas-powered overhead heaters, and you can see the equipment down below being warmed by the overhead infrared heaters. And then a little closer look at these ones here, an infrared gas-fired heater. gas-fired infrared heaters. Radiant heat is used to heat a solid surface. So inside these devices, we have combustion happening, and we heat some kind of a solid surface, and then that solid surface becomes the source of the infrared or radiant energy. The variations on the theme: a surface combustion heater uses the porous or drilled ceramic mat, wire mesh as the emitting surface, and a reflector directs the radiant heat into the area. These are not vented, which means they require ventilation. So if you have a heater like this, you wouldn't be sealing up the building and expecting people to breathe the combustion gas. You need to be in a semi-ventilated exposure to the outdoors. Okay, so unvented ceramic gas-fired radiant heater. So we have a air inlet and a gas inlet and some area for combustion. It heats up this solid surface, and then we get that radiant energy reflected down through the air to the objects below. And here's what it looks like when it's fired up and operating. So if you have a bus stop or an LRT station, you have outside areas heated with infrared radiant heaters. Internally fired are a variation on that, so we can connect them to outside vents. And that would make them safer to use inside a building because we can vent them to the outside of the building. Internally fired vented heater consists of a heat exchanger, metal or ceramic gas mixture is burned in the exchanger, heats the emitting surface, reflectors direct the heat. So the one that comes to mind is this one. This is in the car wash. More and more people are using these in their garage. They're not that costly. They have a tube, internally fired tube. So we bring combustion air into the intake with a fan, and the exhaust is out the other end of the building, out chimney. Gas-fired infrared vented heaters, horizontally internally fired radiant heaters. And there's one that has the fan on one end, and they burn down through this tube, and they come back and exhaust it at this end. Something called a low temperature catalytic heater. I mixed up the slides here, or I lost a slide. Weird. Something called a low temperature catalytic heater. A layer of glass wool is impregnated with catalyst, usually metallic salt. Oxidation of the fuel takes place, burns slowly. We used to use these in tents and campers, and I don't know, I've seen people use them in little construction shacks and stuff, but we probably shouldn't have over the years because they need to be in an outdoor situation. And more and more we see these electric infrared heating, so they're directly powered by electricity, and they create that radiant heat, keeping our occupants comfortable in a very specific area for spot heating. And these electric heaters have nickel chromium heating elements, and page number 9-6 looks at other types of electric heating elements. One is called a metal sheath element. Most everything that creates electric heat has a specific metal called nickel chrome or nichrome. When it's connected to electricity, it has the right amount of resistance. It will glow and create that radiant heat. So 3 different kinds of elements for that: a metal sheath or a quartz tube heater, a coiled nichrome or nickel chrome element enclosed in a quartz tube. And the quartz lamp heater contains a tungsten filament supported by spacers in a sealed quartz tube with inert gas. Now, the important thing about these 3 types, on 9-7, there's a chart with characteristics. So what's some of the things that are important to see and note on that chart, with a highlighter preferably, is they have metal sheath, quartz tube, and quartz lamp. So response time, 3 minutes for metal sheath. Takes a while, but that device has an excellent impact resistance. Quartz tube will heat up in 1 minute, but has poor impact resistance. So quartz tube, basically a gas tube, can create some high temperatures. So that's pretty handy in certain instances. They all have approximately equal element life and important characteristics. Can it heat up in a hurry, or does it take more time? And is it a robust element? Can you throw it in a toolbox, for example? So excellent impact resistant for the metal sheath, but not so much for the glass tube. So metal sheath element has slowest response time. Quartz tube has poor impact resistance, and the quartz lamp heater responds in a few seconds. These are getting popular again. They were popular a while back because does anyone remember McDonald's pizzas? McDonald's used to have a pizza. Some people like them. I don't believe I ever tried them. But their claim to fame was how fast they could make you a pizza. So they developed these special ovens that had quartz lamp heaters. And if you look at that chart on 9-7, it comes up to 4,000 degrees in a few seconds. So if you don't burn the damn pizza to a crisp, you're going to have a key to a good crispy pizza is a hot oven, right? And they could have these pizzas frozen until you ordered them, and they could whip them up in a few seconds with a quartz lamp ovens. And I see they're selling these countertop ovens, small little ovens with quartz lamp heaters in them now. So they heat up fast, so they cook or heat something in a hurry, and they don't use a lot of energy, and really quick response time. Electric resistance heating elements. So if we go back to the heaters like this, open wire type heating element is still nickel chromium, two kinds, open ribbon, a flat ribbon of metal, provides surface for heat exchange, or tubular cased wire. And this would be the tubular case type. I don't know if you can see it in the corner of this one. They have a wire, and when you turn this on, you'll see it glowing inside here, creating the infrared heating. Electric heating can be direct. So all these heaters we're looking at, baseboard heaters, wall heaters, unit heaters, and unit ventilators, radiant panel heaters, heat lamps, and snow melters that are electric cables embedded in walkways are direct heating. Sometimes we have indirect electric heating. So we heat a medium, carries the heat to the area being heated, and that's an application of an electric boiler. So we heat up hot water or steam, and we send that steam or hot water into a finned exchanger or coil and put it in an air duct to warm the air in a warm air heating system. So direct, we have a glowing element heating up things directly. Point this heater at something, it's going to heat it up. Or indirect, we heat up a medium such as water or steam, and then take that medium over to the place we need to heat. A little review of chapter 9. Infrared heating is generally used for big buildings with high base structures. Okay, not so much in any of these. For comfort, we direct that infrared radiant heat to the floor. Infrared gas-fired heaters use what as a source of infrared energy? That's a solid surface is heated up, and then it emits the radiation. Some different ways to do that. One of them is a non-vented infrared heater with a ceramic mat and wire mesh. So that's a surface combustion heater. The gas-fired infrared heaters are surface-fired vented heaters. Okay. Nickel chrome spiral resistor in an insulating refractory in a metal tube. This is the heating element called a metal sheath element. What is it you remember about quartz lamp heating elements? They get very hot very fast. When you talk about an open wire heating element, it looks like this, and it's made of this nickel chromium or nichrome. Electric heating classes, direct or indirect. Direct is a heating element, gets hot, heats up things around it. Indirect is, one example is an electric boiler. There's the indirect electric heating. All the above. Infrared radiant heaters are directed towards the floor. Spot heating is common in areas open to the atmosphere. Just making a note here for a change I want to make. Infrared heating is well suited for buildings with high bay structures. Infrared heater, which has a drilled mat with wire mesh as an emitting surface and not vented, is called a surface combustion heater. Gas-fired infrared heaters use a solid heating surface. Source of infrared energy emitted by infrared heaters is a solid surface. And an internally fired heater is a kind of gas-fired infrared heater. Heating device consisting of a nichrome spiroresistor embedded in refractory surrounded by metal tube is called the metal sheath element. And that's different than a quartz lamp heating element. The quartz lamp responds in a few seconds. Open wire heating element, the resistance wire is made of nickel chrome, nichrome. General groups electric heating can be divided into direct and indirect, and an electric boiler is an example of indirect electric heating. Electric heating, surface combustion heaters. Yeah, this is wrong. This is not electric heating. But there's some good points here. Not electric. Gas-fired infrared heaters use heat. A solid surface becomes the source of infrared energy. Surface combustion heaters employ a porous mat or wire mesh as an emitting surface. Internally fired vented heater is a type of gas-fired infrared heating. If we're talking electric heating, the quartz lamp has the quick response time, heating up in a few seconds. Open wire electric heating element uses nichrome resistance wire. I was working on this late last night. I may have been under the influence of some strong cough syrup. I see lots of typos. Electric boilers are the best example of indirect electric heating. Electricity heats a medium, moves or carries the heat over to where we need the heat. Any questions on electric and radiant type heating? I think we're into 10, and then we're gonna do 11 and pop over to 14. Humidification. Who wants to remember from the video, why do we need humidification? What was the theme of the video? What's the darn difference? No guesses? Proper humidity increases comfort and reduces static shock. Please remember that our book number 2 is basically used to be titled Human Comfort. They don't actually have a inside. They have heating systems and human comfort. So everything in book 2 is about systems that are geared to keeping the occupants comfortable. And I think between ventilation and humidification, those are the top 2 items that are important. If the air is dry, if we use steam especially and or hot water heating, we're not normally circulating air, so we're not doing ventilation, and we're definitely not doing humidification, or usually not doing humidification other than spot areas. And buildings like that can be very, very uncomfortable. If we have wood and furniture, I have grand piano in my basement. And very, 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 very important to keep the humidity up so that that piece of equipment that my wife uses to make a living doesn't dry out and crack and stop working and need to be replaced. Okay, the value of that piano is more than half of the value of my house. Beth bought it in 1971 for about 7,000, but it's worth over 100 grand to replace it now. So, determining relative humidity is important to maximize human comfort. So yeah, we're going to talk about relative humidity, but humidity is important for human comfort. Very important. What is humidity? This is the water vapor or moisture in the air. There might be a video or two coming up, short ones. Amount of moisture depends on the temperature of the air. And we're not really going to consider the change in humidity based on atmospheric pressure, strictly on temperature. Temperature change has a considerable effect on humidity. If the air is warmer, higher temperature air, it will absorb more moisture. If the air is colder, the air will have less moisture absorbing ability. So very important term to have very clear and very straight in your mind is relative humidity. This is the moisture that is contained in the air compared to the maximum amount of moisture you can hold at that temperature. It's important to realize that if we change the temperature, we're going to change this number, and then we have to do something about that. And one of the things we normally do in a cold climate is we're bringing in air from the outside that's colder than what we have on the inside. By raising that temperature, we're going to drop the relative humidity, and then we have to replace the relative humidity in that air. High temperature air can absorb more moisture. Low temperature air has less moisture ability. Higher the temperature of the air, the more moisture hold. Relative humidity drops when air temperature is raised without adding any moisture. So how often in Alberta climate do we raise the temperature of air? We talked about needing ventilation. We talked about doing ventilation. We talked about ventilation being very important. Generally, that involves bringing outside air, which is cooler than inside the building, bringing it in. Now we have to heat it up for human comfort. Relative humidity is going to drop like crazy. One of these is true. Does it remain the same when air temperature is raised? Does it remain the same when air temperature is low? Remember, temperature has a big effect. Okay, so this is not true. Increases when air temperature is raised. That's not true. Decreases when air temperature is lower. That's not true. Relative humidity decreases when air temperature is raised. Considering that we're just raising the temperature, we've not added. So the opposite of dropping air temperature and relative humidity increasing is relative humidity decreases when air temperature is raised. How does that work? Let's have a look at a video, a 3-minute video. I'm going to stop sharing because I need to flip the switch here so you can hear the video. Then I'm going to share again. Sure, it's like a great switch. Now is my video going to work?
You get it? Shit, me too. Me too. What? You can't choose one?
Hello Internet and welcome to Ever Wonder Bits. What is relative humidity? Humidity is just a value for the amount of water vapor in air is holding. And 100% humidity is not pure water, but 100% of the water vapor in air can hold at given time. So what's the deal with relative? You see, air can hold different amounts depending on its temperature. Atmospheric pressure is pretty low, but since we're all experiencing more or less the same pressure, we cannot know. The rule is hot air equals more water than cold air. 1 cubic meter of air at 30 C can hold up to roughly 30 grams of water, while air at 10 C can only hold up to roughly 10 grams. I say roughly because the amount isn't linear corresponding to the temperature. The real curve should look like this, but 30 grams and 10 grams makes it easier to hold. So for the remaining video, I'll plot the roughly. Filling up the air with the maximum amount for a given temperature raises the relative humidity to 100%, and we have reached the dew point. Everything above 100 isn't able to stay inside the air and will condensate into water droplets, giving us things like morning dew, fog, rain, or annoying cold blasts. But how can we reach such high levels of humidity? Remember, relative humidity is linked to the air temperature. If we take, for example, air at 30 C with relative humidity of 33% and cool it down to 10 C, the humidity will rise to 100%. Cooling it down from warm would oversaturate the air, so water will compensate. Again, I'm simplifying. An example would be opening the door of your refrigerator. Warm, humid air will blow in and start to cool down. This lets the water condensate, showing the ice on the walls. If you come inside on a cold day, when gases cool down the surrounding area, getting them hotter. And the other way around, if you get some away from the sun, warm air can easily absorb any water, and if the wind is blowing the saturated air away, it will dry even faster. See you again. Have a good one.
Okay, I'm gonna go through this quite a few times because it's pretty darn important to understand the concepts. So, 100% relative humidity. This is the volume of air that is saturated or has reached a dew point, and this is outside air at 10 degrees C. And a given volume of air can only hold so much moisture at this temperature. Doesn't matter what the numbers are. We talked about some numbers. We'll look at some numbers as we go through. If we take this 10-degree air and we double the temperature, what happens to relative humidity? Does it go up or down? Yeah, it's going to go down. And it's if we double the temperature, guess how much it's going to go down? It's going to be about half as much. Okay. In this volume of air, we still have the same amount of water, whatever that amount is. But if we double the temperature, we increase the volume of the air, so there's less water, which means there's a lower relative humidity. So if we bring that same air into the building from 10 degrees outside and we continue to heat it, when we get up to 30 degrees C, probably you wouldn't go that high in your building, but our relative humidity is going to drop. It's going to drop some more. The same amount of water vapor is in that air, but the volume of that air is greater, so we end up with less relative humidity. When we bring outside air up from 10 or lower in Alberta, it's unlikely we're going to be as high as 100% relative humidity. We have very low moisture in the air normally. It's probably going to start at 28% relative humidity. So by the time we get into here, we're only going to be 14%. Comfort zone for humidity is recommended to be, and I'm just going to pick a random number. I sort of like 40. And I'll tell you why. There's some things in the book that are going to tell you. Here's a chart on 10-4. It says recommended relative humidity if our outdoor temperature is minus 18. We should shoot for 30. If our outdoor temperature is a little warmer, we're going to shoot for 40 plus. So somewhere between 35 and 45 is a pretty good number. If you start to get somewhere around 40, you're probably gonna, what are you gonna find in your building that's gonna be problematic? Some of this moisture in the air is gonna condense on the windows, and it's gonna freeze and frost and melt and drip into the walls and cause all kinds of problems, okay? So as much as humidity is a good thing, More than 40 is likely more comfortable for human occupants, but anything more than 35 to 40, you're going to get problems with excess condensation. Okay, there's another video here. This is a longer one. This is a good one. It's recommended. It's quite a bit more technical, but this fellow does give a good explanation of relative humidity and changes in temperature and stuff like that. Okay, to kind of sum that up, relative humidity at 100%, air at 21. If we have 100% relative humidity, it can contain 0.015 kilograms of moisture per kilogram of air. If that air is colder, such as 5 degrees, it can only contain this much moisture at 100% humidity. And if air is very cold, such as -18, there won't be a lot of moisture in it. So relative humidity is going to be quite low. We're going to bring in outside air inside our buildings. We're going to need to heat it up. Then we need to add some humidity. If a 1 kilogram sample of air at 21 degrees C contains 0.0075 kilograms of moisture, that's only 50% relative humidity. So as soon as we start conditioning the air, heating it or cooling it, these numbers are going to go crazy. Reminder what the definition is. Relative humidity is defined as the amount of moisture contained in the air compared to the maximum amount the air is capable of holding at that temperature. And relative humidity, we call it RH, and we express it in percentage. When air is heated without any additional moisture, that relative humidity drops. We often draw in outside air, which means we drop the relative humidity. Health authorities suggest between 35 and 50. I suggested 40 is kind of, that's what's attainable here. When I'm looking after that piano in the basement, I shoot for 40 and I generally keep it around 40. Because if it's too much, it can cause condensation on the windows for sure. Sometimes it will occur in the walls, and then that can be problematic in the construction of our building. And one way to gauge that is just simply look at the window corners in the cold weather. Signs of condensation means the building humidity is too high. And this is a chart from 10-4, different temperatures, different relative humidity. How do we make up humidity in the building? In a residential system, we have 3 types: atomizing or wetted element or pan type. We'll look a little closer. Residential humidifiers. So basic, back in the day, we had a pan sticking into the duct in the warm air type system. It had some plates that absorb moisture. And when the airflow moved through the ducting, it went through between these plates and picked up some moisture. It's a shallow pan that's partially filled with water. There's a valve here that admits water to fill this pan a little bit to get some humidity happening. So that's a shallow tray partially filled with water. We'll also look at the wetted element, and then we'll look at atomizing, and we'll look at some other commercial type. Pan type humidifier used in the plenum or ducting of small furnaces, a shallow pan with vertical plates. Pan is partially filled and the plates absorb water, and this is called hygroscopic plates. They soak up water and then they evaporate it or liberate it into the plates as the warm air passes over the plates. And there's a float valve to maintain water level in the pan. And this is not the best. This is, you'll rarely see this kind of system. There are pan type humidifiers that are big industrial units that are in use, but it's a different system than this simple version. Wetted elements have type humidifiers have a fan or bypass type, so they can be connected from the return air to the supply air across the furnace, and air will flow through and pick up moisture from flat or cylindrical elements also in a tray. So part of this will fill with water and evaporate water into the airstream. Wetted element have 2 types. They have the power type the fan, or the bypass type, simply connected across, return air to supply air. Atomizing type, just simply have a spray nozzle, and when we turn on some water, it will spray into the airflow. Atomizing type humidifier. I've seen these in industrial use. I've never seen these in a residential setting. Two kinds of atomizing. Spray nozzle is the one we looked at, or one that has a spinning disc. And we're basically breaking up water, atomizing it into a mist or fog. They atomize the water into a fog that's absorbed by the air, sprayed into the supply ducts or living spaces controlled by a solenoid valve. Humidifiers, humidistats control the solenoid valve. Any questions on how we put moisture back in the air? Okay, atomizing humidifiers can leave a fine white dust in a room, so we spray water into the air. This is not necessarily pure water, it's likely tap water. The impurities in the water are going to evaporate and then settle as a white dust in the rooms and in the ducting. Industrial and commercial. So we're going to look at air washers and steam grid units and briefly look at some industrial pan type humidifiers. Air washers are versatile. Their main purpose is humidification, but they are wonderful because they can also heat, they can also cool, dehumidify, and they clean the air. So the name of it, air washer, means it can clean the air. And if we manipulate some parameters within the unit, we can get some cooling and dehumidification. What is an air washer? It's casing with a spray chamber. So there's multiple spray nozzles inside a chamber. This is part of a ducting. In a system, we have airflow going through. Bigger units will have more spray nozzles. Water is spraying inside this unit. The air contacts the spray water as the air flows through the unit. Eliminators or baffles to prevent droplets in the air coming out. We want to evaporate the air into the airflow to increase humidity. We don't want to get all the ducting all the way down the system soaking wet. So eliminators, and then this one has a basin at the bottom. Air is spraying through the air and washing down, washing the air and collecting in the basin. Air washers, true or false? 3 true and 3 false. Air washers can humidify, also dehumidify. Air washers can heat or cool the air. Air washers will clean the air. We're spraying water through our air. It's certainly going to pick up dust and dirt and make it cleaner. These are not small systems, so they're in big systems. Do they remove greasy particles and soot? Apparently not, according to the textbook. And not the best for tobacco, smoke, and odors. What's the best air cleaning unit for tobacco, smoke, and odors?
Outside.
Say again?
Outside.
Oh, yeah, that's right. Keep it outside. So true or false, air washers can clean it, can humidify or dehumidify. Air washers can heat and cool, and air washers can clean the air. This is not what air washers do. Okay, and this is the same one. Air washers can humidify, air washers can heat, and air washers, when in operation, water is spraying, they're always humidifying. If we heat the spray water above a certain temperature, the heat will transfer to the air, so we have heating action. It's not going to be the system that heats the air to the building, but a fine adjustment in temperature can be done. How do we control air washer spray water temperature? So to heat the water, to allow us to heat air with an air washer, we can do it in different ways. Part of the spray water is recirculated. Hot or cold water is added as required. Spray water is circulated through a heat exchanger, cooled by chilled or heated. And another method is a heating or cooling coil directly mounted in the sump. So we'll look at an air washer. We have air coming in, we have air going out. We have some eliminator plates. Here's our water spray, spraying a lot of water through our air. And a basin in the bottom is collecting that water. It's being pumped through an exchanger and then goes back up to be supplied back to the spray inside. So if we heat the air, we're going to add temperature to this air. If we cool the air, we're going to reduce the temperature, cool it down, and anywhere in between, right? We can adjust the temperature by adjusting the temperature of the spray water in the air washer. Cool and dehumidifier. So if we have cooling action going on here, this is cold water being sprayed. Cooling of air will reduce relative humidity. And that's how we can use air washer to dehumidify. But we have to cool the water circulating around the sprays. So this one has cooling or heating exchanger or swinging between heating and or cooling and dehumidifying. This one has a heat exchanger with hot or cold water supply to control the spray water. Okay, why do we humidify? So review of chapter 10. Why do we humidify? For human, mostly for human comfort. Dry skin can be a factor. When humidity is high enough in a heated building, people will feel warmer at a lower temperature. So the cool sensation of skin evaporation is reduced, and also important to reduce static electricity. Definition of relative humidity: moisture contained in the air compared to the maximum amount of moisture the air can hold at the stated temperature. As soon as we change the temperature, the relative humidity is going to change. Heat the air, relative drops. Cool the air, relative increases. Relative humidity decreases when air temperature is raised. Okay. Relative humidity does not remain the same when air temperature is raised, does not remain the same when air temperature is lowered. Does not increase when air temperature is raised, it decreases. Does not decrease when air temperature is lowered, it decreases when air temperature is raised. Okay. Warm air heating systems, placing a single humidifier in the furnace. Plenum could be a pan type. This is a shallow tray partly filled with water. We have two wetted element types, a power type and a bypass type. And the atomizing type uses a spinning disc or a spray nozzle to break the water into a mist or a fog. Okay. Disadvantage of an atomizing type: we just spray water into the air. It can create the mineral or salt deposits from the dissolved minerals in our city tap water. Air washers, they do lots of things. They can humidify or dehumidify, they can heat or cool, and they can also clean the air. This is a repeat. Okay. Can they humidify? Yes. Can they heat the air? Yes, under certain conditions. Air washers can humidify, air washers can heat. By heating the spray water to temperature above dry bulb temperature of the entering air, we can have a net effect of heating the air. And how do we set an air washer up to cool? We cool the spray water below the dew point temperature of the air. Okay. To control air washer spray water temperature. So in the book, page 10-8. Starting on page 10-8. Gray water is collected, recirculated when air washer is used for humidification or cooled, or methods to maintain spray water at desired temperature. 3 different methods. So part of the spray water is recirculated, hot or cold water out as required, or spray water is circulated through a heat exchanger, cooled by chilled water or heated by hot water, or heating or cooling coil directly in the sun. Make those adjustments and changes to the temperature of the spray water. Temperature. Any questions on spray washers? Air spray washer. Okay, 10-9. Steam grid humidifier. If we have steam, we can use steam for humidity. This is when we have pressure around 35 to 70. So hot enough air, hot enough steam to be sprayed into our airflow just to humidify it without causing excess humidity, or sorry, condensate to be created in that system. Control of steam done by a modulating valve activated by a humidistat. So 10-9 shows steam grid humidifier, a very simple one with a pipe with holes in it, control valve that is not recommended to be on and off, because if we put a bunch of steam in, it's going to spike the humidity, and then we shut it off, it's going to drop. So they're recommending a control where we vary the amount of steam. And there's that simple steam grid humidifier. Okay, any questions on chapter 10? Chapter 11 is actually, I'm going to take just a 1-minute break here. My wife had to go out tonight and my mom is alone. I just got to poke my head out the door, reminder that we've not abandoned her. So I'll be back in less than a minute.
Hola.
Yes, sir.
Teacher's back. Okay, how's everybody doing? Short chapter on controls for heating systems. And then a little bit of looking at lighting. 5 chapters, but we won't Probably won't be late. But we will have covered lots of stuff. Lost a couple. So electric controls for heating systems. Watch the language. This is not necessarily electric heating systems. This is how we control heating systems. These are controls for steam heating systems. These are controls for hot water heating systems. These are controls for electric heating system. These are controls for any type of heating system. Because it says electric, it doesn't mean it's electric heating. Okay, something to keep the old brain aware of. Okay. Electric control of heating systems. So control of all kinds of heating systems. What do we do to control systems? We start and stop the flow of current or vary the voltage and the current between a controller and some device. These devices, these controls could use line voltages of 120 or 240 volts AC or lower voltages provided by step-down transformer, generally 12 to 24 volts. Why electricity? Why do we use electricity to control heating systems? Usually we have electricity, we have it readily available. We have these voltages around in the plant, in the factory, in the area, in the buildings. And then with a transformer, it's really easy to get a lower voltage or some smaller amount than 120 or 240. Wiring is generally quite simple and easy to install compared to pneumatic control or control by air signals. It's kind of old school for industry. Signals received from sensing elements can be used to produce more than one output. So signals might have to go to multiple places. Very relatively easy to make a multiple output. You simply parallel an electrical output and supply that signal to many places. And then there's lots of flexibility. Controller and actuator combinations are eminently possible, different combinations, and we don't need to have a main air source that you would require by sort of older school pneumatic or air powered control systems. So some of the things in the glossary for chapter 11, an actuator. This is a device that positions or moves dampers and control valves. Contact arrangement is talking about electric switch configurations such as relays or switches. Control valves are used to control the flow of liquid or gas, and control valves are used a lot. Controllers, this is a device that will react to different things. For example, temperatures, pressures, humidity, flow, level. And this will provide different sorts of electrical outputs, such as two-position, something called floating or proportioning control or modulated type control. Dampers control the flow of air and the ducting, line voltage, normally 110 or 240. Linkage, something connecting an actuator to a damper. So we have dampers, but a linkage is something between the actuator and the damper, or a control valve. If we're using 30 volts or less, we will often call that low voltage, but some plants I've been in, low voltage is anything below 700. So we're going to call 30 volts extra low voltage. Relay is a device consisting of a solenoid that operates contacts, so a specific type of electric switch. And transformers, if we need to step this voltage down to a low voltage, we're going to use something called a transformer. Thermostats are basic controller in any kind of a heating system. We're going to sense the temperature in the room, and we're going to hook it up to some other kind of controller, and we're going to turn things on, turn them off, increase or decrease the output to supply the heating that we need. Different kinds of thermostats, they can be classified by application. type of sensing element, temperature range, type of action provided, and if you see this list in the future, I would pick all of the above. A thermostat's function is to maintain the temperature of a heated space or substance at the desired level. Temperature of the heated space is maintained at the desired level by controlling a heat supply. So our basic controller for a heat supply, whether it's steam or hot water or electric, is this simple thermostat. We have different kinds of thermostats. Remember, this is something that maintains a set or desired temperature. We'll look at bimetal, we'll look at remote bulb, we'll look at a type of remote bulb called the aquastat. We'll see thermostat that fits into a duct, and we'll talk about modulating and multi-position thermostats. Bimetal has different metals expanding and contracting to move the contacts in a bimetal thermostat. Remote bulb thermostats use some kind of volatile liquid to create the control action that we desire. If a thermostat is immersion type, it is sensing and controlling the temperature of some sort of liquid that it's immersed in or inserted in. Multi-position has two or more switches in sequence, and we will look at these one at a time. Bimetal, so two types of metal, different metals bonded together, sitting at a cooler temperature will have a close contact. Should this metal bar be heated, it will expand at different rates, the two types of metal. And when it opens the contacts, that's the set point of the thermostat, and that will turn off the heat supply. Different metals expand at different rates. Longer strip has more free end movement. So if this is a longer bimetal thermostat, it's going to move more out at the end here. On a rise in temperature, so cool temperature over here, temperature rises, it opens the contacts to turn off the heat source. Remote bulb thermostat. So this one has a long capillary tube with a bulb at the end. There's a bellows inside the housing, contains volatile liquid in the bellows and the bulb and the tube. And when this liquid is heated and expanded, it increases in pressure, expanding the bellows, and operates a switch through a lever. The principle of that one is contains a volatile liquid which expands when heated. So bellows in here, remote bulb type thermostat. Variation on that is this one. It has the same bulb connected to a bellows. Heated liquid increases the pressure, expanding the bellows to operate a switch. So as this thing gets heated up, depending on the set point here, this one here has a set point, some way to set a temperature. It will turn off the power through electrical contact. Thermostat that is inserted in a duct, it controls air temperature in the duct or plenum. Modulating thermostat uses some sort of variable resistor to modulate the control system. So we can have an increased amount of heat or decreased amount of heat modulated to control temperature where it needs to be. As opposed to a multi-position thermostat. So this is a thermostat with two mercury switches. And as this device is heated up, it will move the first switch into contact to turn on a first stage gas valve. If it continues to move in that direction and needs to turn on the second stage gas valve, it will heat more. Multi-position uses two on-off switches, so sequential switching on of the heating system. Where do you put a thermostat? Should be installed where it will sense the average room temperature, recommended to be about 1.5 meter above the floor, and some places here where you don't want to have hot things in the room interfere with the thermostat. If we are controlling a humidifier, we use a humidistat. A hygroscopic element will control humidity in the room. It will pick up higher humidity and shut off a humidifier, and it will pick up lower humidity and turn on the humidifier. Okay. Pressure controllers. So another type of controller in the heating system. We'll move the dampers in our ducts. Pressure controllers 11-8. Two classes. There's high pressure controllers and low pressure controllers. So if we have pressures in the kPa range, we're going to call that a high pressure controller. And if we're down in millimeters of water, we're going to call them low pressure controllers. Examples: high pressure controllers will control steam or water pressure in a HVAC or AC system. Low pressure controllers will measure and control air pressure in a duct. More sensitive to low pressure. Generally, you can see a controller for very low pressures is a large device because it needs a very big diaphragm to react to very low amounts of pressure. Lead type static pressure controller is described on 11-9. It's just a kind of a basic primer on pneumatic controller. This doesn't really even come under electric controls, but there it is in the chapter. Electric radiator valves, motor operated valves, and three-way valves. These are controlled devices. Okay, some examples of controlled devices: fuel valve, diverter valve, damper motor, or electric relay. So all of the above. And this is the same question: fuel valve, diverter valve, damper motor, and electric relay. And a longer list on the next page: motor operated valves, electric relays, electric radiator valves, three-way mixing valves, three-way diverter valves, damper motors, operating louvers. Some pictures. So a valve controller, this is actually air operated. This is a damper motor for controlling gas and air flow to a furnace. This is a damper motor for controlling ventilation air into a 6-inch duct with an actuator on the side. 11-11 describes three-way valves that are used for mixing or diverting service. And this is an example of mixing. So bypassing the boiler and mixing to get a required temperature. Three-way valve installed for diverting service. So we have a supply. We're going through a heat exchanger, but when things get hot enough, we're going to initiate a power supply to a three-way valve and bypass the flow, so there's no heating. Capacitor type motors, two classes: one for valve operation and one for damper operation. Louver type damper motorized controllers. So different types of motorized controllers for moving dampers. Next slide is the glossary repeated. And I think the next slide is the same. Yeah. A damper controls the flow of air in a duct. A linkage connects an actuator to a damper. An actuator is used to position a damper and or control valve. And a transformer is something we use to change AC voltage. This is not air conditioning. This is AC voltage as opposed to DC voltage. We have an electrical chapter coming up in one of the later books. More stuff about electricity. Okay, to position dampers and control valves, we use an actuator. Actuator is a device to position dampers and control valves. Classifications of thermostat, all of the above. It might be the range, it might be the type of control, it might be the application, and it might be the type of element. Thermostat classifications, all of the above. Types of thermostats, remote bulb is one type, uses a volatile liquid. Immersion type senses the temperature of the liquid. Multi-position has 2 or more switches to sequence multiple devices. And the principle of a bimetal thermostat is different metals expand at different rates when heated. Where do you put a thermostat in the room? Where is it recommended?
Where you'll get the best toughness for the room.
Yeah, and that's kind of eye level, right? 1.5 meters above the floor. Temperature rises. What will a bimetal thermostat do? The strips bend and open the contacts to stop the heat source. Remote bulb thermostat does not have mercury or alcohol, but it has a volatile liquid. What is the sensing element of a humidistat? Something called a hygroscopic element. Classes of pressure controllers, high and low pressure. Not flow, not temperature, not this one. Pressure controllers, high and low pressure class. Okay, what about high and low pressure? High is in kPa and low is in millimeters of water. Thermostat senses air temperature. Okay. Electric radiator valves, motor operated valves, and 3-way valves are control devices. Control devices, all of the above: fuel valve, diverter valve, damper motor, electric relay. And now we're going to dive into chapter 14. That's going to give us some extra time on Thursday to start our review. Losing people. So when we come back on Thursday, we're going to look at building water supply systems and sanitary drainage system. Should cover that in less than an hour, those 2 chapters, and then move forward on our book 2, part 1 review. Okay, lighting systems. Let's go to chapter 14. Many slides in chapter 14. Too many. This is a Mickey Mouse chapter, but it will take long, folks. Lighting systems. How do we light up our lives? Some of the stuff in this chapter is kind of outdated. There's newer technologies, but most of the principles are important. And important things, initial costs, operating costs, maintenance costs, so all of the above. When designing a system, you must, are you going to design the system? No. Illuminaire. When you go in a building and you look up and you see a light fixture, from now on, you're going to call it a luminaire. This is a lighting unit. This is a source of light, or the lamp. It might be incandescent or fluorescent or LED, or in some cases halogen source of light. There will be some sort of electrical equipment to control that current and control for startup of this fluorescent or LED lighting. And then there will be control of light. This is not the on-off switch. The on-off switch will be in the hallway on the wall somewhere. The control of light means there's going to be reflection and refracting of the light. And I have pictures. Function of a luminaire: it directs or controls the light produced by the source, and it does that with refraction, reflection, and absorption, directing the light to areas where it's most required, where it's needed, and preventing light from going into areas where it's not required. If we don't need light, we don't need to produce the light. We can direct it where we need it, and then reduce our costs. So lighting costs are big. Here's the light control methods in a fluorescent. fitting. So we have some kind of light source. We can have reflectors, and the light will bounce off a reflector and go in a different direction. Sometimes it's refracted. Sometimes it's also diffused, and we'll look at the different parts that do these things. So here's our source of light. It's being reflected and refracted, and with the intent purpose of spreading it around the room. In most cases, we have general area lighting. We want this light to go all over the place, all around, all the different directions. And sometimes we're going to concentrate the light for spot lighting. So we're just going to put light exactly where we need it. So sort of your common, normal luminaire. We're not going to call this a light fixture anymore. We're going to remember that it's a luminaire. Looks like this. It's called a recessed troffer. Troffer refers to the ability for this to fit in to a hanging ceiling. Hanging ceilings or suspended ceilings are very popular. They're very practical. They're able to suspend our lighting systems, give us a good light colored surface to spread the light around, and then the ability to get in behind there to change wiring and check on piping and move things around. So typical recessed troffer. Sometimes they're wraparound, they drop below the ceiling and they give light off the sides. Occasionally we'll see reflector type troffers. These will have more light going down and less light going off to the sides. Cove or indirect lighting will be hidden behind some architectural feature to give us a softer, more calming type of light. Types of illumination, something called general uniform, something called local or supplementary or combination. General, local. General is just strictly classroom type lighting, uniform throughout the area. So we'll see these guys, multiple fixtures all over the classroom, spreading the light all over the place. So general, uniform illuminations, spacing is uniform, offices, schools, classroom. There might be additional or local or supplementary lighting, such as work area or display lighting, a wall wash or spotlights, track lights hanging down over a work area or workbench where you want additional lighting. Some combinations in the textbook about conversation in the textbook about combinations, combined general, local, non-uniform or task lighting. So types, reminder types can be general, which is uniform lighting all over the place, or just local task lighting, put the light where you need it. And then some combination of local and general. Ambient lighting can be improved by direct and indirect. So some combination of all these things might be the best lighting. So ambient lighting improved by direct and indirect is more energy efficient than all indirect. Indirect lighting is less bright. So if it's all indirect, it's not going to be as energy efficient as direct lighting, but supposedly there's less glare and equals more comfort in the lighting department. To improve ambient lighting, provide direct or indirect or a combination. Remember that direct is just all light directed onto the work area, and it's considered the most efficient. Indirect, reflected first by ceiling and/or walls and more comfortable and has less glare. How do we control lighting? We use different kinds of switches, variety of switches, usually just on and off control. 2 40-volt circuits may require 2-pole single throw, so there's different switch configurations here. Something called low voltage lighting. In the older buildings in NAIT, they have switch panels inside the rooms. My father-in-law was an electrician. He had a big dream home he built on an acreage. When you went into a room in his house, there was 6 different switches, and they were the same type as in the hallways in the older rooms in NAIT. There's one switch there that will turn on the general lighting in the room. There's a switch there for just the lights at the blackboard at the front of the room. And in some cases, there's a switch for some indirect lighting or some focused lighting. And at my father-in-law's home, he had variations, valence lighting behind the valences over the window. So soft lighting, you could push a switch for that, or you could push a switch for spotlights, hot lights in certain corners and highlighting certain pieces of switches of furniture, or you could push one switch and everything came on to light up everything. And he had a panel in the hallway when he was going to bed. If he didn't want anybody to be up or wandering around, he could hit one switch that would stop all the lights in the whole house. Or if he got up in the night, he heard a intruder, he could hit one switch and all the lights in the house would come on. All the lights downstairs, all the lights on different floors, all kinds of combinations. And that's an advantage of using a 24-volt switching system. You can have cheap wires and multiple switches to give you all kinds of local control, remote control. So buildings wired like that were set up that lights could be left on at the end of the day. Cleaners come in after the end of the day and they're going through the rooms. When they get to the end of the wing that they've just cleaned, there's one switch there that kills all the lights in the whole ring. So that's what this low voltage lighting is about. The loads or the circuits are controlled by relays. Local and remote control achieved by using switching circuits that are low voltage, and changes are simple and economical. I don't know why they say this in the text. They most definitely not, but of course, that being said, I'm not an electrician. So low voltage lighting, changes are simple, economical. Wiring is not in conduits because it's just low voltage, long runs of writing. Because of relays, we can have all kinds of control and different possibilities. This is a diagram of how that works, the low voltage stuff. Circuit breaker switching, a little bit about circuit breakers. Photoelectric controls, cadmium sulfide photoelectric cell responds to varying light conditions with varying internal resistance. So these are lighting circuits for the street lights or outside lighting on the building. When it's dark outside, resistance is low and the lighting comes on, and in daylight, it will open a relay and turn the lights off. So simple daytime, nighttime control of outside circuits. And that's the circuit described in the textbook. Sometimes lighting is on timers. Something that's fairly common in the newest buildings, they always have occupancy sensors. These are automatic switches that sense motion. So if somebody comes in the room, the lights turn on. If you leave the room empty for a time, the lights will turn off. The newest areas in the newest buildings, there will be sensors in every light fixture. As you walk down the hall after hours, it will come to normal brightness, and after you pass down the hall, the lights behind you will dim and then go out. So there will be this moving field of practical light where it's needed based on motion sensors or occupancy sensors. Two types, infrared respond to heat signals and ultrasonic respond to the motion in the room. And in reality, the new ones actually have combination sensors. Okay, if you have a simple ultrasonic or air motion switch, people in a classroom can be quietly working on their lessons, and the lights just keep going on and off. People have to wave their hands to put them back on. So a combination infrared and ultrasonic keeps the lights on. So ultrasonic type, infrared type. Dimmers, we used to dim the lights for various reasons, thinking it was saving energy, but resistant dimmers are not energy efficient. They work on variable resistance. Emergency lighting, critical circuits are kept alive should there be interruption of current flow, a failure of the electrical system, or any general power failure. A little bit about luminaires that recover heat. Cold weather, the heat from the lighting can be a benefit. So these are light fixtures that have luminaires. We're not going to say fixtures anymore. These are luminaires that have provisions to remove the heat, to improve efficiency. So by cooling the ballast, we extended its life, cut our maintenance costs. something that is mentioned, I think in the book at the beginning of the chapter is lighting can be 60% of the electrical cost. So you can imagine a complex such as Nate, the tens of thousands of dollars spent on keeping the lights on, right? If we can save energy in the lighting, we can save a lot of money. So the heat removal fixture luminaire is supposedly looks better. Heat can be reclaimed, efficiency is increased, and we can decrease cooling and ventilation if we can get rid of the heat created in the luminaires. Energy conservation and lighting, correct level of illumination. So that's why we have different types of lighting. If you only need light over the workbench, that's the option you have. That's the way you can avoid wasting light. When we talk about efficiency, we talk about lumens per watt, and different lamp types have different ratings. So a high lumens per watt is going to be an efficient light source. Okay, incandescent, old school, not very efficient. Mercury vapor, a little better. High pressure sodium, a little better. Low pressure sodium is better. There's a chart here, shows those relative efficiencies. High efficiency fluorescent ballasts use less energy and produce less heat. So they last longer to save money, right? Saving energy and producing less heat, use a high efficiency fluorescent ballast. The biggest bang for your buck in lighting maintenance is plan relamping. When we know the life of our lamps, we plan to start changing them. This saves labor. A couple of electricians change every lamp in a room. They can do a whole room in a day, as opposed to one bulb goes out, you write a work order, he waits 3 hours for a permit, changes one bulb, 2 or 3 people these days. Cost benefit is just change them and change them all on a regular basis, and cleaning. So they can change the lamps and clean the fixtures and save more money than other methods of energy reduction. Occupancy sensors can save money, so lights go out when no one's there. High efficiency lamps, fixtures, balance, save energy and produce less heat. Using task lighting where possible, that cuts down on lighting everything up. Some other energy conservation points. 3 reasons for emergency lighting: interruption of a circuit, failure of the system, or general power outage. Should be a page number here. This is near the end of the chapter. Scared myself when I opened that configuration. Emergency lighting, where is that? $14.11. Life safety code requires emergency lighting is provided in all educational and institutional occupancies. Quick review of chapter 14. Complete lighting, we're going to call that a luminaire. Designing a lighting system, all of the above. Capital costs, operating costs, maintenance costs. Direct lighting is more efficient than indirect lighting. Low voltage switching, all of the above. Changes to control wiring are simple, allows for local and remote control of lighting. Control wires do not require conduits. Cadmium sulfide cell varies resistance with light intensity. This is for street lights and building lights on the outside. Occupancy sensors are automatic switches. Resistance type dimmer switches do not save energy. Advantages of a heat removal luminaire. Ballast life is increased. Lamp efficiency and ballast life is increased. Heat removal luminaire improves the appearance, heat can be reclaimed, lamp efficiency is increased, decreased cooling and ventilation, and ballast life increase. Measure of efficiency of a lamp, lumens per watt. High efficiency ballast, save energy and produce less heat. Most effective maintenance for electrical lighting systems, group relamping and cleaning. Okay, right on time. How was that? I kept most of you awake or disappeared. That's okay. We have a recording to fall back